working right away. That's surprising. Alright, so this is where we left off last time. And you can see the nice trend that we get when we're talking about attractive forces. So if we have more strings binding something, it's going to be bound tighter, right? It's going to be harder to rip it away. So if we have more London dispersion forces binding something, it's going to be bound tighter. There's going to be stronger forces attracting the two things. And so it's going to have a harder time boiling, i.e. it boils at a higher temperature. Okay? It'll also have the same trend for the melting temperature. So it would melt at a lower temperature. It would, as we go lighter here, it's going to melt at a lower temperature. As we go heavier here, we're going to have a higher melting points, higher boiling points. We'll have lower vapor pressures. You already kind of knew this because right here, that's natural gas. Natural gas is mostly methane with a bit of ethane and a little bit of propane mixed in. Okay? And so, you've never seen liquid or solid natural gas, have you? Propane, on the other hand, is negative 42. You've probably never seen liquid propane, but if you had a very high pressure tank, you might. Okay? Butane is actually the lighter fluid in your lighters. What do you see about the boiling point right here? It's negative 5 degrees Celsius, isn't it? So an interesting little factoid about butane lighters. So you go to the grocery store, you go to the pump, right? And you see those little lighters, and they have a clear bottom. They have liquid in them. That's butane liquid. Okay, it's a liquid because it's under pressure, right? And if you were to go out in like South Dakota, North Dakota during the winter times, Alaska, and try to use a lighter, can anybody guess what would happen? It's too cold. It won't actually light. So you'll get the sparks, but you won't get a constant flame. And what happens is, if you've ever seen it, you've probably seen it on movies and shows and stuff, where they're out in like the field of snow, and then they take the lighter, click, 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 doesn't work, and they like stick it under their armpit, or they put it in their chest and like hold it up to their chest. And what they're doing is they're warming the lighter. Once you warm it up past 0.5, negative 0.5 degrees Celsius, the lighter will have gas in it. Whenever you click it, it'll give you a stream of gas, and that's what you actually burn. Okay? Up here, this is actually things like gasoline. Isooctane is the octane rating for gasoline that burns like isooctane. Okay? This stuff up here would then be like your diesels and such. And if you go to C20-ish, that's where you'd start seeing things like your waxes. Okay? Anybody know what you're doing when you light a candle and you put the lighter in there? It doesn't start burning right away, does it? So you have to like wait for it to go to liquid, and then actually what you're doing is you're vaporizing some of it. Once you start vaporizing it, that's when it lights. And that's when the candle starts sustaining its own ignition. Okay? You actually have to do the boiling point. That's what you have to reach. Okay, so let's look at predicting the vapor pressure and boiling points for different alkanes. So if you have more molecular weight, that's going to give you a higher boiling point. That's going to give you a lower vapor pressure. Okay? Now, if you're highly branched, that's going to shift that boiling point, melting point down, and it's again going to give you a higher vapor pressure. So right here we see the hexane. It has a boiling point of 69 degrees Celsius. Right here we have the same molecular weight, but now we have branches. Can everybody see that okay? It's branched instead of straight chain. And look at what happens to the boiling point. It goes down to 58 degrees Celsius. Man, I can't even read my own. Can you guys read that? It's super blurry, isn't it? Anyways, 58 degrees Celsius. I could have just kept it with 59, couldn't I?
Well, I'd have the presentation up and I'd call you as a liar then.
Okay, fair enough. You should too.
Okay.
No. Yeah, there is no way to actually make that less blurry, is there? That is something. Okay. It's just gonna have to be blurry, I guess. Yeah. The presentations are online if you ever want to see it non-blurry. It's pretty high resolution online. All right. I take the figures directly from the manufacturer. Same figures in your book. Full resolution. Okay. So, again, melting points and boiling points, they follow the same trend. The reason that these things follow the same trend is because they have stronger intermolecular forces are going to keep them from melting or boiling until higher temperatures. Easy way to think about this is if you have very weak magnets and you try to pull them apart, it doesn't take a lot of energy, right? And so that would be like having a low boiling point. It takes very low energy to pull them apart and throw them off, right? If you have very strong magnets between these and very strong attractions, then it's really hard to pull them away, isn't it? And so you need much higher temperatures to do that, to break those interactions and throw them up into the gas. Okay? Okay. So we have several different types of molecules that we're going to start talking about. And we have the non-polar molecules, right? These are those London dispersion molecules. And the big determinant on those of how large their boiling points are is going to be the molecular weight, how big they are. And then the other determinant is going to be how well the surface area contacts. Okay? So if they're straight chained, you'll have lots of surface area. If they're branched, you have very little surface area, right? Okay. If you have similar sized molecules that have different attractive forces, then you're going to have these stronger attractive forces have higher boiling points, right? Higher melting points. This is why, for example, gasoline versus your water, water boils at a higher temperature, doesn't it? Gasoline boils at a lower temperature. Okay? If we start going into something much more extreme, like salt, table salt, those are ion-ion forces, right? So they're very strong. And so you notice you've actually never seen melted salt, have you? Unless you watched Discovery. And they covered the salt reactors. It's probably the only place you would have ever seen melted salt. Very, very high forces to start melting salts. Okay? Lava would actually be an example of the sort of temperatures that you're melting salts. Okay? Minerals would be very similar to a salt.
Does it actually melt, or does it just immediately change?
A little bit of it does melt.
Wow,
but for the most part, it's actually you just have heated it so much and put it under so much pressure that you start having the solid flow.
Yeah, okay.
Yeah. And that's why if things get on top of it, they don't actually sink. It's because it's incredibly dense.
Interesting.
Yeah. So if you ever fall in lava, you don't sink into the lava. You would, in fact, it would actually feel harder than the ground here. So, like, it would take more force to push through lava than it would push through this. Okay? Because this is not very strong. You all know this is like wafer board, right? Yeah. And so, like, lava is very dense, pretty hard, actually. It seems liquidy because it's under tremendous pressures. Yeah. And that's actually why it kind of flows-ish a little bit. There is a little bit of liquid, though, in there. And some of the minerals will actually liquefy at lower temperatures. So there's actually some really crazy stuff going on in geology right now. They found water down in the Earth core.
What?
Yeah. Yeah, where the diamonds are formed.
Liquid water?
Yes. Yeah. And so it's because it's so much pressure that it's this super high energy liquid water.
That's crazy.
Yeah, it's insane. Yeah, there's some really crazy stuff going on in geology right now. So this is molecules with the same attractive forces. So if we're looking at the same attractive forces, like a water versus a sugar, one of the other things you have to start looking at then is how many of those connections can make. Okay? So one of the things that makes water so good at storing energy, and another way of saying that is have a pretty high boiling point, actually, considering its hydrogen bonding, is it can make two hydrogen bonds. rather than just one that some other things can make. Okay? So again, these are those steps that I've just went through in terms of predicting the vapor pressures and the boiling points. Now, one of the things that may interest you all more, is most people are more interested in like biology and biomolecules, is that these are actually what give all the biomolecules their shapes. So the attractive forces that we've talked about are the same ones that hold all the different biological molecules together. So for example, cellulose molecules are tightly held together by hydrogen bonding with their neighboring molecules. And so that's how you get those clusters of cellulose, actually. They're hydrogen bonds there. The London dispersion forces are actually what hold your cell membranes together, and that's the force responsible for your cell membranes. Your overall shape of the cell is held together by a combination of your cell membrane forces, the London dispersion forces, and some proteins that help to maintain that shape. Okay. The hydrogen bonding is actually responsible for the double part of the helix. So the double helix is entirely held together by hydrogen bonding for your DNA. The overall shape of it's actually also held together by hydrogen bonding, but different hydrogen bonding. Okay, which I won't be able to show you on the figure that we'll look at next. The protein structures, these are actually a combination of all the forces we've talked about. Do you guys remember that ionic salt bridge I mentioned? That's actually what's responsible for holding parts of proteins together. So it has the ionic salt bridges, it has ion dipole interactions that help maintain the structure of your proteins. It has London dispersion forces. There's like large nonpolar London dispersion force regions inside proteins that help hold their shape. There's hydrogen bonding within the protein that helps hold its shape and make the different alpha helixy structures. And so we actually use all of the forces I've talked about here to maintain protein structure. Now, one of the reasons that this is really interesting, because when you start talking about biology, the structure, the shape of the thing is its function. Scissors don't work if they don't look like scissors, right? If you were ripping apart a pair of scissors, that's not scissors anymore, would it be? Okay? And so that little screw is responsible for the scissors working, isn't it? And again, these intermolecular forces are what are responsible for the shapes of those proteins, the shapes of those biomolecules, and the shapes are what are responsible for them functioning. Okay? This is why, for example, if you get 70 degrees Celsius, all of your, you start hurting really bad. Anybody gotten above 70 degrees Celsius and put their hand under the water? It starts hurting, right? It stinks. Yeah. And if you let your body temperature get above 70 degrees Celsius, that's actually where you start accruing damage. Okay? And the reason you're accruing damage is you start breaking these intermolecular interactions. That's why you're getting hurt, is you're actually breaking the intermolecular interactions for your different proteins, cell membranes, etc. Okay. And so you're destroying their structure, and so they no longer can function. Okay. Just like if you destroyed the structure of this building, it would no longer function as a building. Okay. Right here we have the double helix of the DNA. These right here are the two helices. Everybody see those okay? Okay. And the things that holds them together here, see those little patterns of 2 versus 3 versus 2? Okay. Those right there are these bases. Okay, those are called base pairs. And they're being attracted together by hydrogen bonding. Okay. Is everybody familiar with the AT-GC base pairs for DNA? Okay. Okay. So the reason that they're keyed together, AT matches, GC matches, is actually the hydrogen bonding here. This is a GC match. And see how it has 3 hydrogen bonds that overlap in the correct distances and correct orientation? And that's what caused them to be able to match and bond. If you get an A trying to match with a C, it's not going to match because it only has 2 hydrogen bonding. Okay? And they aren't going to quite be the right orientation, but they'll be pretty close actually. Okay. And so this is actually what causes that base pair matching that you may have heard of, like ATGC. And that's what causes your DNA to be able to replicate. That's what causes your double helix structure for your DNA. All of that is just hydrogen bonding. Okay? Even the helix structure is actually due to hydrogen bonding, and interestingly enough, London dispersion force is holding this structure together into that twisted structure. There's actually 3 different types of twisted structure that can take on because of that. Yeah. Whoa, huh? Yeah. It's the bases. See how these are very big bases here? If you stack them on top of each other, they experience London dispersion forces.
Makes sense.
Yeah. Okay, so let's talk about the golden rule of solubility. How do I figure out if something is soluble in something else? Okay. Now, you may have heard, hopefully you've experienced in your life, oil and water don't mix. Okay. I can never take anything for granted anymore. Sugar, water, they mix, right? That's Kool-Aid. That's sodas. It's all around us in the United States, isn't it? Everywhere you look. Everybody knows sugar and oil and water, right? You can get like salad dressing. Those salad dressings you have to mix up first, like the vinaigrettes. Those are oil and water. Okay? You can't actually get them to dissolve into each other, can you? The other example of oil and water, everybody's been to the gas pumps, right? Okay? When it freshly rains, what do you see in the little puddles? You see the water, and then on top of it is the shiny surface, right, that has the really beautiful coloring. It is pretty. And that's the gasoline. And that's because the gasoline does not dissolve into the water, right? And so it just sits on top. Okay? All right, so we're actually witnessing there the solubility in the case of sugar and water. In the case of like gasoline and water or oil and water, we're seeing the insolubility, the lack of solubility, right? That they do not dissolve. And so, how much you can dissolve into a given substance is the solubility. So if we're talking about sugar, it is very soluble in water because you can dissolve lots of sugar into water, right? If we're talking about like alcohol in water, like ethanol in water, then it's what's called miscible, meaning you can dissolve any quantities into each other, okay? And if we're talking about the solubility of like oil in water, that's extremely low, typically referred to as insoluble, okay? Now, that golden rule for the solubility is going to be like dissolves like. This is the easiest way to remember it. So if you have a similar type of intermolecular interaction, if you have similar intermolecular attractions, those are going to dissolve well into each other. So if both of them do hydrogen bonding, like sugar and water, right? Bless you. You're going to see them dissolve very well into each other. Okay? If you have something like gasoline and oil, and anybody want to try to guess what would happen there? So gasoline, oil, both are going to be what are referred to as non-polar, right? They don't have poles, and so they'll mix pretty well. Yeah. And if anybody knows any mechanics, that's like an old trick to remove oil. Is if you get oil all over your hands or parts or whatever, you take gasoline in a pan, and you can actually dissolve the oil off. Yeah. And so it's an old trick to remove oil. It works quite well. Really does. Considering gasoline is usually less harmful than the oil you're removing. So it is the similarity can actually be simplified a bit if you're looking at these things. And so you can actually simplify it by saying polar and nonpolar. So your London dispersion forces, your ones that do not have permanent dipoles, those are going to be nonpolar. Okay? The ones that have permanent dipoles, those are going to be polar, right? So if you have two different charges in two different spaces, those are polar. If you don't have a charge on both sides, that's going to be a nonpolar one. No poles, right? Okay, so we can discuss that same things we looked at before. The gasoline and oil, those are nonpolar substances. So they dissolve each other, but they don't dissolve into like water or polar substances, right? That's why like gasoline doesn't dissolve sugar well. Okay? If you were to, you can also experience this if you've ever put sugar into oil before. you're trying to cook different sugary things, you notice the sugar doesn't actually dissolve in the oil. It just plops in the oil and burns up usually. Yeah. So if you've ever tried that out, that's that. That's why you can like fry up starchy things and get those nice crunchy chicken fingers or whatever you're making. Yeah. So again, if we're looking at the sugar versus water, right, because of all the hydrogen bonding on the sugar and the water, well, those are both polar. They can both dissolve into each other, right? Okay. That's the OHs are polar. So I've already covered the polar versus nonpolar. Now we can actually simplify this a bit more, and we can say, does it dissolve in water? Okay? So this is the level below this in simplicity, right? Which is that we have hydrophilic, philic means to love or loving, and hydro meaning water, right? And so it's water loving, hydrophilic. And that means it dissolves in water, okay? Basically, these are typically going to be polar things, right? The hydrophobic, phobic meaning phobia, hating, right? And so they are hating water, hydrophobic. And so these are going to be things that are not soluble in water. And for the most part, that means nonpolar. Okay? And so here we have the terminology to say, hey, does it dissolve in water or not? Okay? And you've probably heard this before and seen this on commercials and stuff. Your special hydrophobic coating on your shoes or pants.
I was just looking for that stuff for my son's shoes because he keeps ruining them.
Oh, yeah. You can either buy the shoes with them or get the spray.
I want the spray.
The sprays don't last quite as long.
They don't, but
Yeah.
whatever. He's ruins his shoes too fast.
Still might be worth it, yeah. So let's predict those solubilities for our nonpolar compounds. So again, if we look at oil again, oil would be a long organic structure. It has a long organic carbon chain, right? And so it's nonpolar. If we look at water, that's polar, right? It has a hydrogen-oxygen bond. It has a permanent dipole on it. One side's negative, one side's positive. And so these are unlike each other. We have polar versus nonpolar. They won't dissolve well, okay? If we were to look at table salt is ionic, right? We have a positive charge and negative charge. It will dissolve in things that are polar fairly well, won't it? Because they have positive and negative charges, okay? If we were to look at a nonpolar substance like gasoline, oil, cooking oil, probably the one you've seen the most. Hopefully you're not throwing a table salt into gasoline. Then what we would see is that salt, when you put your salt on your food while you're trying to fry it, well, that is polar with a nonpolar, isn't it? And so the salt does not dissolve in the oil, does it? Okay. All right, so again, this would be an example of a polar compound. This is actually a disaccharide dissolving in water. And see all of those little hydrogen bond acceptors and donor areas? So this is why disaccharide sugar dissolves fairly well in water, right? Is we have lots of hydrogen bond donors and acceptors all around the water, all around the sugar that can donate or accept to the water, right? Everybody see those okay? So that dissolves quite well in water. Now, right here we see table salt dissolving in water. Now this is an ionic compound. It's going to have a chloride, which is negatively charged, a sodium, which is positively charged, right? And so what's going to end up happening is the water molecules are kind of coming along the sides, edges, and corners, and they're going to start attracting these individual ions. So the positively charged sodium right there, the cation, is going to be attracted to the negatively charged oxygen on the waters. Okay? That's eventually going to pull it away from the salt crystal. And so you'll see parts of the salt crystal slowly start disappearing. Okay? And what's going to end up happening is the sodium here is going to end up what's called hydrated, meaning there's waters around it, making a little cluster or shell around that sodium ion. with their negative charges associated with the sodium. Now, once you're hydrated, then the outside layer is just water, isn't it? So it's just going to do its normal hydrogen bonding from there, okay? An interesting side note to this is water is actually really structured. It's like 80% highly structured, okay? So if you were to actually look inside water, it looks more like a snowflake than you'd probably predict, okay? It's actually quite structured. And when it freezes, it gains that extra 20% and it becomes very structured. Yeah. Your typical liquid water is actually more structured than you probably think. Okay. This right here is going to be the chloride portion of the table salt. And so you'd have the hydrogens, which are positive, associating with the negatively charged chloride. Okay. And they're going to pull that out of your crystal structure and then surround it, and that's going to be the hydrated chloride ion. Okay. And that's how you actually dissolve things. You may notice, has anybody ever taken like cold water? You got just directly, it's winter, and then you try to put like salt in it and get your salt water for like boiling pasta? And it doesn't dissolve well, does it? No, it dissolves very poorly. Part of that is because to actually cause salts to dissolve, you actually need energy to break them up. So if you keep it really cold, you can actually start getting salts that even though they'd be soluble, they won't dissolve. It'll take them a long time to dissolve.
It's like increasing the salinity of the ocean up in the Arctics.
Yep, that actually happens.
Yeah.
And in fact, one of the reasons that happens is that the very cold water up there doesn't dissolve it very fast, and then the ice forms and actually excludes out the salt. So you can get like little salt deposits.
Yeah.
It's pretty wild. Okay. Now, this is actually a huge deal when we're talking about drugs. Has anybody ever heard of something called the blood-brain barrier? Okay. So the blood-brain barrier is because the blood is made of what? Water. Mostly water. Yeah. The vast majority of the blood is actually water, right? And so when you're talking about your brain, well, the brain is made of cell membranes, isn't it? And so you have cell membranes, nonpolar, and then water polar, right? And so to get a drug to disperse throughout the body, typically you have to make it soluble in the blood, don't you? But to get it to actually do something, you gotta get it to go into the cells. And the cells have nonpolar environments around them, okay? And so you usually have to play a little bit of a trick with most drugs, where they're going to be polar for a little while. They'll get outside that environment into the blood, and then they'll go back to being nonpolar or less polar, so that then they can go through the cell membranes. Okay? And so you do have to, this is always a worry every time any drug is discovered that has any effect. How are we going to deliver it? Okay? It's a huge part of the pharmaceutical industry. About 85% of all drugs are administered orally to be absorbed in the digestive tract. These drugs, if they're absorbed in the digestive tract, have to be water soluble because they're going to have to be distributed through your blood. Okay? The only way you can avoid that is to literally stick a needle in somebody right where you want the drug and then put it there, right? Which they do sometimes, but it's definitely the harder way to do things, right? Now, more than 40% of new chemicals that are discovered by the pharmaceutical industry as potential therapeutic agents are actually insoluble in water, and so they are not appropriate for giving people orally, which is the vast majority of the pills that you would want to give somebody, of course. And so what you do is you play a game. You add a carboxylic acid or an amine to it. The carboxylic acid is an acid, so when it gets in a basic environment, it's going to protonate and it'll become highly charged, right? That's going to make it more polar. The amine, on the other hand, when it gets into the stomach, which is an acidic environment, is going to protonate, and that's going to become positively charged. And so that's going to make that water soluble. So those are two different ways you can make something water soluble. Then when they get into a more moderate pH environment, you start seeing more of the drug become neutral. Now, this does mean that there's a fairly large amount of the drugs that you take that you actually just urinate out a fair amount of them. Yeah, you'd be shocked about how much of the drug you actually waste. But usually it's not a huge deal because they're very potent drugs usually. The actual dosing you need is very small for most drugs. In fact, the size of the pills is typically because they have to dilute the drug so much just so they can reliably mix it out. They can measure it out reliably. Yeah. Most of the size of the pills is usually a binding agent. Typically like something like cellulose. Okay, so this right here is one example of this, and you actually kind of knew this if you ever read your medicine bottles at all. So you typically will see if you read the medicine bottle, it'll say like .HCl, or it'll say hydrochloride on it. And this is what they're doing. So they're taking the drug right here, it has this amine, right? And they're putting it with HCl, and they're giving you the salt. Okay? And so what they're actually doing is they're giving you the salt of the drug. This is soluble in aqueous environments, and so when you swallow it, it'll start dissolving in your saliva, and then down in your stomach, and then down in your intestinal tract, and that's when you'll get that in your blood system. Okay? When it gets back onto the blood system, this will start neutralizing, and more of this is going to fall out as a neutral and go into your cell membranes. Okay? Everybody got that okay? Okay. So this is one example of a legal drug doing this. In case you're curious, yes, this is also the same way that difference between cocaine and crack. The exact same thing. Because cocaine used to be a pharmaceutical agent that was used. Do you guys know what the big difference between pharmaceutical agents and illegal drugs usually is? Okay. It's a combination of two things. The one that you probably all thought of is addictiveness, right? Yeah, if it's physically addicting, that's usually bad. But most pharmaceutical agents, and most illegal drugs are also physically addicting, aren't they? Yeah. So the biggest difference usually is availability. Once something is physically addicting and easily available, that's when the problems really start happening. That's why, for example, heroin was originally a pharmaceutical agent. Morphine, still a pharmaceutical agent. And heroin, actually, they're thinking about bringing it back because it's so cheap to produce and so powerful. So, like, end-of-life care, it actually makes a lot of sense. But, yeah, that's why, like, fentanyl, it's been a pharmaceutical agent for over 50 years, widely used. Now we're having huge problems because it's just so easily available. Yeah. So, if it's hard to get your hands on it, then it doesn't take off as an illicit drug, right? Which, I don't know, there's good things about things being easier to get and bad things about easier to get. And we definitely have seen the bad things with fentanyl, haven't we? All right, so this is your fatty acids. Notice your fatty acids do have carboxylic acid. And so this part right here is polar, isn't it? But your fatty acids also have these long nonpolar chains that are typically like 10 to 20 carbons long. And so that part's nonpolar, isn't it? And so this is referred to as amphipathic compounds. Amphi means both. Pathic means condition. And so these are compounds that have both regions, one region being polar, one region being nonpolar. Okay? Whether they dissolve in water or not is going to depend on which region dominates, which one is larger, okay? Which one has more effect on the forces you're looking at. So and when we're talking about fatty acids, typically this fatty acid nonpolar chain here dominates because it's very, very long and very large. So it'll drag it out of water. Soaps, however, are actually fatty acids that have been converted to salts. And so what you do with a soap is that is a fatty acid that you've put in with a base. And so it deprotonates it right here, puts a little metal ion to attach to this, and makes an ionic head. Okay? And so they're going to be ionic because they have the carboxylate with the hydrogen removed from the carboxylic acid, functional group at one end. And they're going to bind something like a potassium or sodium typically. And it's going to make this very ionic head. And then they have this long nonpolar hydrocarbon tail. And that's going to be extremely nonpolar, right? So we got the polar head, nonpolar tail. These are amphipathic. This is what soap looks like. So again, we have the carboxylate head right here. That's going to be the polar ionic one. And down here we have that nonpolar tail region. Everybody see it okay? Okay, you often see soap written out like this with the charged head, nonpolar tail cartoon representation. Okay, now, again, remember, these are not like forces. This is London dispersion forces right here. This is going to be ion dipole forces up here. Okay? So very strong ion dipole force, and then lots of London dispersion forces down here. Now, what's going to end up happening here when you have a bunch of soap molecules together in water is they're going to form something that's called a micelle. Anybody ever heard of a micelle before? Mm-hmm. If you've taken biology, you definitely have. Very, very common in biology. They're formed essentially the same way. The molecule is very similar to a soap molecule. It just has the ionic portion incorporated into the head and attached, so it's a little harder to remove. So they're very, very similar in a biological setting to the soap molecule. So, okay. So when you put them in water, they're going to make a micelle. Has everybody seen the double layer membrane where we have two outsides to the cell membrane? Okay. This is only going to have one outside. It's not going to have a double layer. Okay? So it's not going to have two outsides. So this is again going to be the hydrophilic heads all point outwards towards the water. The hydrophobic tails are all going to point inwards towards each other. And it's going to make this micelle right here. Everybody see the micelle okay? Okay. Now, what would happen if we had something else nonpolar in here? Let's say some grease. What would happen here?
Hold on to it.
Yeah, these nonpolar tails would all cling onto it, right? And so your grease would get surrounded by these nonpolar tails, and the polar heads would all point outwards in a sphere, and then the water can lift it and wash it away, right? And that's how soap removes like grease from your jeans or your hands, right? Okay. And so that's why you normally use soap. So again, these are going to be that golden rule. So greasy dirt's not soluble in water because that is nonpolar. And there's a lot of biological agents that are also nonpolar, and you need to use soap to remove. And so again, they are going to have the nonpolar tails are going to cling to that nonpolar grease. It's going to develop a shell around it. That shell is then soluble on the outside, and it's going to lift it away and allow it to go off. Okay? Now, those amphipathic compounds like soaps, these are typically called emulsifiers. What's going to happen here is that this is actually not dissolved in the water. This is a very large structure, right? It's very heavy. Look at those water molecules compared to this. They're really small, aren't they? If you were like a person, would it be okay to like have one person support something that's like 30 people around? No, it's going to drop through, right? And so the same thing happens with the waters. If you just let this soapy water sit there, the soap is actually going to sink to the bottom eventually. It'll take a long time, but it will happen. Okay? And so emulsifiers make emulsions. Emulsions are similar to you mix it up, it mixes, and then they fall out slowly. Very slowly, okay? And so again, that's these. This is an emulsifier. That's soap. Is an emulsifier. Okay, how do we predict the soluble in water? So we look at these two different things. This is vitamin C and vitamin E. Okay. This right here. See all these OHs on it? That's mostly polar, isn't it? And so this is going to be hydrophilic, isn't it? It's going to be water-loving. It's going to dissolve in water. we look over here and we see we have a few polar things, but over here, the vast majority of the compound is nonpolar, isn't it? See that? That's vitamin E. This is not going to be water soluble. Okay? This is in fact what's referred to as fat soluble. So this is a fat soluble vitamin. This one right here is a water soluble vitamin. Okay. Has anybody heard you need to continuously get vitamin C in your diet at least once every 2 days? Okay. The reason for that is it's water soluble. So if you eat vitamin C, if you take in vitamin C, you're going to urinate it out. And within 2 days, you have the vast majority of your vitamin C is going to be urinated out, gone. Okay? And so, if you don't get vitamin C every about 2 days or so, your levels are going to plummet. Okay? Now, what can be caused by a reduction in vitamin C? Has anybody ever heard of scurvy?
Mm-hmm.
Like the old sailors, and you see it in the movies all the time. They're like bent over like this, bleeding gums. Yeah, that's scurvy. It's actually a disease, but if you have low levels of vitamin C, you are much more likely to catch it, and you're going to have a harder time fighting it off. And do you guys know what the leading population who catches scurvy is now in the United States of America?
The elderly?
It ain't sailors, it ain't the elderly. It is college students.
That's right.
Yep.
Living on top ramen and pizza.
Yep, that's exactly why. It's because the college students get out from the thumb of their parents, right? And their parents used to be like, drink your orange juice and eat this fruit. And they don't do that anymore. And so they start eating pizza all the time. And usually it's like cheese or pepperoni pizza, right? And ramen. And none of those things have vitamin C in them. Okay? You'll be fine though if you just drink some orange juice works. Even Sunny D works, though Sunny D is terrible for you. Also red peppers. So if you order your pizza with red peppers on it.
And strawberries.
Strawberries work, yeah. There's actually quite a few sources of vitamin C. And a lot of the drinks now come fortified with vitamin C, so it's fairly easy. Basically, if it's like fruity-ish, it usually has vitamin C in some degree. Because people are trying to help you out. People are. This one right here, fat soluble. If you eat this once a month, you'll typically get enough. Yeah. By the way, that's why they put, like, if you ever look at the back of a vitamin C thing, they give you 1,000 times your dose you need. So it's 1,000% or 10,000% of what you need a day. They're trying to make it so if you take it once, you'll last for like 4 days instead of 2 days. It's actually a little concerning because, I mean, even vitamin C can be toxic to you at some point.
Mm-hmm.
Yeah.
Are you familiar with the powder things, the emergencies that have, like, you said, yeah, my husband will drink like several of those a day. I'm like, are you trying to kill yourself? Stop that.
Oof.
He's like, I'm sick. I'm like, that's not going to do. Don't do that.
Yeah, there's going to be diminishing effects at some point. Does he do zinc?
Mm-hmm.
Anyways, this one's fat soluble, so it stores in your fat along with your fat, right? And so you can store it up, actually. Okay? Now, that doesn't mean that you can chronically not eat vitamin E and be okay. You do have to, get your full dosage eventually, but it does store up. What is the difference between fats and oils? Well, this is actually an outcome-based measurement. If at room temperature, it is a solid, it is a fat. Okay? If at room temperature is an oil, then it is a liquid, it is then an oil. Okay? So these are the nonpolar compounds. Fats are going to include things like steak, lard, butter. These are typically derived from animals if they're natural. Technically, we process things that would normally be oils and make them into things that would then be fats. For example, technically peanut butter would be a fat. Peanut butter is actually an oil, which we have hydrogenated to make it a solid at room temperature.
What about coconut oil and...
Yeah.
Because it's like that.
No, it's a fat.
Solid and...
Yep, so it's a fat.
Yeah.
Well, it's right on the edge,
It
but
is.
it's normally a
Like
fat.
78 degrees, it'll melt.
Yeah.
in.
Yeah, so the room temperature is actually 25 degrees Celsius. I believe at the official room temperature, it would actually be in oil.
Okay.
But it is right on the edge. And there are plant fats.
Right.
Like, they do exist. They're kind of rare, but they do exist. Yeah. Yeah, so.
Or olives.
Yep, they're definitely plant fats. Oils, these are going to be mostly things like the corn, soybeans, peanuts that are derived from plants typically. Again, there's oils in animals as well. We have oils like on our skin. So, like, there are the other ones. It's just the majority of oils you're going to get from plants, the majority of fats you're going to get from animals. Okay? That's the overall trend. Now, fats and oils, these belong to a class that's called hydrolyzable lipids. They're going to be the triglycerides. Determining fat and oils is just as simple as at room temperature, is it a solid, is it a liquid? Okay? Oil is a liquid, solid is a fat. Okay, so this is actually why this happens between fats and oils, in case you're wondering. So has anybody ever heard of saturated versus unsaturated fatty acids? Okay, so this is what hydrolyzable or triglyceride fats and oils look like. So they look like this. This is the glycerin. So glyceride comes from this name right here. Okay, and these are the acetyl groups right here. You can see that they look like those carboxylic acids a bit, right? We've actually seen those a bit. They're ester linkages. And so what we have here is the fatty acid chains down here. And see how they have 3 of them? That's where the triglyceride comes from. 3 fatty acids. Okay. And so if we look at the straight chain saturated ones, we can see that they're very linear and straight chained, right? And so they overlap really nicely with things. And so they're going to have very strong London dispersion forces that are happening, right? And that's going to make them melt at a higher temperature, okay? If we have a double bond, on the other hand, see that double bond right there in the middle? See that kinks the entire structure, doesn't it? Okay? And so they're not going to stack nicely on top of each other, are they? That's going to make those melt at a lower temperature. That typically makes an oil. So for example, right here, we actually see an oil. See, it has several of these cis double bonds. This is an unsaturated fat right here. All 3 of these are. And this is going to be further apart. It's not going to stack as nicely. And so this is going to make that an oil. Okay? It's going to melt below room temperature. This, on the other hand, has much more straight chains because it's saturated fatty acids for the most part, with only one unsaturated one. And so this one's a fat. They're going to be like closer together, going to overlap better, giving you better London dispersion forces, and thus a higher melting point. Okay? Okay. So this right here, these are unsaturated cis. See how they're on the same side of that double bond? That's the unsaturated cis fatty acid. Okay? If they were on opposite sides, which doesn't happen much in nature, that's extremely rare in nature, then that's going to be the trans fatty acid, right? Most trans fatty acids in your diet are going to happen because we'll take something like this, an oil, and we're going to do what's called hydrogenation. And so we're going to take hydrogens, try to add them across all those double bonds, and convert that into a fat, like peanut butter, margarine, okay? We take a unsaturated fatty acid, we try to hydrogenate it to get rid of all the double bonds, and convert that into a saturated fatty acid. So that has a higher melting point. And that's why peanut butter is a solid at room temperature. And so you take the peanut butter, we've done that enough so that it's solid at room temperature, you put it in your mouth, and it partially melts. And then you get this flavor explosion, right? By the way, you can get similar flavoring if you just take peanut oil and spread it on and then fry the things. Yeah. It's actually quite pleasant if you've ever not had it. Anyways, this right here, now if you do this with hydrogenation because of the reactions, sometimes they come back and you get the double bond again. And so typically you end up hydrogenating at something that looks more like this, where you have a double bond still. However, on the hydrogenation process, sometimes that double bond comes back as a trans double bond instead, where they're on the opposite sides of the double bond. And that's where we end up getting like trans fatty acids in margarine, okay, which is where you've probably heard them most from. All right, now, again, if we look at those models, we can see that the saturated fatty acids are going to have more London dispersion forces. They're going to lay down on each other much more nicely. Now, the straight chain tails allows for a lot of surface contact. It'll increase the attraction between the tails, and it'll restrict the molecular motion. If you have them attracting heavily, you're not going to be able to move around as much, right? If we have less attraction, then we're going to be able to move around more, aren't we? Okay? And so when you're talking about something like a cell membrane in your body, you actually want to form what's called a semi-solid. And what that means is it's a solid, but it has a lot of mobility. Okay? That your cell membrane actually moves around a lot. Right? And so the stuff in your cell membrane is in constant motion, moving around on top of your cell membrane. Okay? And you do this by mixing together a variety of straight chain saturated fatty acids and unsaturated fatty acids. And so your body very carefully sort of modulates in this little band where it gets it stiff enough so it doesn't just go pop because it's liquid, but it gets it liquid enough that it can move around, because it needs to be able to move around to do things like butt off micelles and deliver stuff to other cells. And to accept things in it needs to be able to move around. So there's a lot of important processes that needs to be semi-solid to achieve. Okay? If you go either way, you're actually going to have a lot of problems with your health. Okay? Too stiff is actually usually, that's where cholesterol comes in actually. So cholesterol is a stiffening agent that your body puts into cell membranes to increase the stiffness of them. Okay? And so you can overdo the cholesterol, get too stiff. You can also underdo the cholesterol, in which case what normally happens is your body tries to make more cholesterol then. If you're having problems with the stiffness of your cells, it's not stiff enough. And then if it overdoes the production and it doesn't do it quite right, you start getting plaques because they start clogging up. Yeah. That's actually what's happening when you have like heart disease. It's not actually because you're eating too much fats. You can limit the amount that you're producing by limiting the fat intake. It's because you already have damage your body's trying to heal. Typically little micro tears along your arteries and veins. But there's a number of different things it could be. But that's usually the biggest one I've heard. All right. Let's talk about the next. So if we look at these different fatty acids, we can have a polyunsaturated fatty acid. And so we saw one where it was just one unsaturated, right? And so that'd just be unsaturated. If we have multiple of them, that's going to be polyunsaturated. Okay? Technically, you can actually use the same language we've used before. If it's two unsaturated, two double bonds, it'd be diunsaturated. Most people don't bother. Just say polyunsaturated. Typically, they start doing that at, everybody does it 4 and more, but a lot of people just start doing it at 3, 2, and just start doing polyunsaturated right away. Again, that kink makes them have less London dispersion forces when they all line up. Okay, now we're going to look at phospholipids, which are actually what are used in your cell membranes, okay? So a phospholipid is going to be a little bit different than your normal triglyceride. It has a lot of the same parts, but there's a few differences. So this is going to have a glycerin backbone with the fatty acids linked to it through an ester bond. That's the exact same as the triglyceride, okay? It's only going to have 2 fatty acids linked to that glycerol backbone, though, not 3. Okay, so it's not a triglyceride. That remaining OH group is actually going to have a phosphate-containing group bonded to it. And that's where the phospholipid comes from. So lipid, like a triglyceride, with a phosphate group attached. Okay. That phosphate-containing group is actually ionic. And so that's where we actually throw in all that polar behavior that we were talking about, like with the soaps, right? And so it's going to have very similar behaviors to those soaps. The fatty acid tails are going to be nonpolar, and so it's going to be amphipathic, like the soaps were, and it's going to have a lot of the same sort of behaviors, okay? Now, these are the fatty acid tails right there. Right here, this is the glycerol backbone. And then we have this right here, which is the phosphate head. And see how it's highly ionic here? Okay. That's going to be your polar portion. That's going to be the portion that's attracted to the water, right? These parts are going to overlap with more fatty acid tails, okay? The big difference here between a phospholipid and soap, though, is we have two tails. See how we have the two tails instead? So if you have two tails, you can't line up as close together, can you? One tail you can line up much closer. Two tails you can't. And so what ends up happening is the double tails make very large structures that would be like micelles, right? But they're so large that the water's pushing on them a lot. So what ends up happening is you actually end up with a double layer membrane. So you get one layer that's pointing outwards, and another layer points inwards with those ionic heads. And that will give you a stable structure then. So that's the lipid bilayer, or cell membrane. Okay. And so, there's many different phospholipids. I've given you this overall structure. There's actually quite a few different ones. We're not going to go into all that. We just don't have time in a single semester course. That would be quite wild, wouldn't it? The two tails of the phospholipid are going to affect the overall shape of your molecule. The phospholipids have a much more cylindrical shape rather than a wedge shape, like you would have seen for the soap molecules, right, with the single tail. And so this is going to change that ability to form micelles. And so your cell membrane is actually going to end up as a bilayer because it's just too large once it arranges itself to support its own structure. Okay? Everybody's probably tried that before with like a thin sheet where you're trying to make like a tent or something and you got to prop it up and support it better, right? Or else it starts getting pushed in. So again, that's that double layer. It's called a bilayer because it has two layers. The polar heads will be directed towards your aqueous environments that will be outside and inside of the cell. Your nonpolar tails will be directed towards the interior region of your bilayer. And this is going to be that cell membrane that you associate with your cells. So this is what a cross-section of that would look like. We have the aqueous environment outside the cell. We have our bilayer here with the fatty acid tails pointing towards each other. And then we have the aqueous environment inside the cell. And so this would make a complete sphere with a hollow inside with water and a outside with water, right? Okay, so protein molecules, these can span the bilayer. That's called an integral membrane proteins. Or they can be associated with a hydrophilic surface of the bilayer. And that's going to be what's referred to as a peripheral membrane protein. Proteins are going to be the membrane's functional components, so they're going to allow selecting cells to move in and out of the cell. Molecules, to move in and out of the cell. They can do signaling functionings. They can do all the different functions you'd expect out of a cell, really. The exterior surface of your cell membrane is also going to contain carbohydrates. These are going to act as little signaling flags. And so that's the things like your ABO blood types. Okay. In case you're wondering, the rho factor, which is the plus minus, the negative, that one's actually a protein. Okay. But there's actually more than just the ABO blood types that have carbohydrates as your signals. There's more to it, but there's no way I can cover all that. So the fluid mosaic model, this is going to be little icebergs of proteins that float sort of in a sea of lipids. And so you're going to see like these little icebergs floating around, and you're cell membrane, and they'll do the different functions. This membrane is fluid-like, and so those phospholipids will move freely within the bilayer, and they'll continuously exchange. They actually can do some pretty crazy stuff like flips and stuff, as long as you have the proper cell membrane proteins, helping them out. And they will be semi-permeable. So, for example, if you have small nonpolar compounds, they'll be able to go through, for example, CO2 being the big one. That's probably the most important. O2 being another one that can go through a cell membrane. Right here again, we have our cell membrane. This is that fluid mosaic model. See the little proteins and carbohydrates and stuff. They're all floating around the outside and inside. Okay. These yellow things right here, those are cholesterols, helping to stiffen that up. This is what a cell looks like. We have our cell membrane right here. Then we have our cytoplasm, which is the aqueous environment inside the cell. And then right here we have our nucleus, which is another membrane just like this one. Very, very similar. We actually have several other membranes within the cell, but we won't be able to go into all those. So please take like microbiology or something. Yeah. It's worth taking. It's interesting. Okay, so let's talk about steroids and membranes. So cholesterol is a steroid, and it's sort of the simplest steroid, if you can think of it as that way. This right here is what the nucleus of a steroid looks like. So this structure is what all the other steroids are based off of. Okay, and which includes cholesterol as one of those steroids. And so see these 6-membered rings here, series of 3 6-membered rings, and a single 5-membered ring right here. Now, notice that this structure is very different from the fatty acids and triglycerides, right? Even though they're different, though, this is still classified as a lipid because it's still nonpolar. Okay? These molecules, they have a variety of functions in your body. They can regulate sexual development, like, for example, testosterone, estrogen being the big ones. They can emulsify dietary fat, that's your bile acids. They can be cholesterol, which helps to stiffen your cell membranes, and a few other purposes. Cholesterol actually contains your steroid nucleus right here. You can see that yellow part. And then we have a few extra parts. We have this little polar end here. So what happens is cholesterol situates itself in the phospholipid bilayer. This OH is actually what protrudes into the aqueous environment. Okay? And so you can see it's this little kind of weird analog of what like fatty acid would look like, right? Yeah. Now, this can slip in between the saturated hydrocarbon tails, and so it can actually increase the fluidity when you have the saturated hydrocarbon tails. It can interact with unsaturated tails, increasing the rigidity, and so it does this nice little balancing, where if you have too much saturated, you'd normally be too rigid, right? But if you have too much saturated, cholesterol will actually cause them to start binding to each other as well. And so you'll actually get a more fluid structure. If you have a lot of unsaturated fatty acids, and so you'd be too liquid, all of a sudden this actually helps going the other way. It helps the binding of those and makes it more rigid. And so cholesterol is this mediator that you put in those cell membranes to help you balance it. Okay? There's a few other mechanisms that you can use to balance your cell membranes, but this is probably the most interesting one and the one that's easiest to understand. And in general is like the biggest one, I would say. Yeah. So kind of a cool thing, right? You got your cell membranes being modulated. That's actually the end of the chapter right there. You know what? We can just call that a day. As a reminder, if